So thank you all for coming. I'm amazed so many of you are interested in such a sort of esoteric topic as this. So if you're just waiting for the next speaker, then that's fine. So I'm going to talk to you about simulating CPUs, sort of CPUs with Python, sort of Python, and to try and convince you that this might seem like an extremely silly thing to do, and hopefully, but it is a doable thing to do. So if you all leave here still thinking it's a silly thing to do, that's fine, but I want you to believe that it's tractable. So I'm going to start off by saying a little bit about the particular chip that I've mostly written a simulator for. You probably all know by now that chips are not going to get any faster anytime soon. So if we want better performance from machines, then we need to exploit things like parallelism. But there's lots of different ways to make code parallel and lots of different ways to make machines parallel. And people have tried all sorts of various configurations of chips and cores and different things, some of which have worked, very many of which have not worked. If you've been to one of Russell's talks, you will know that very many of these ideas have not worked. And if you haven't been to one of Russell's talks, ask him in the lunch break. So the chip on the right or the board on the right contains the chip that I'm writing a simulator for. So this is the chip. It's called the Adapteva Epiphany. So the simulator is called Revelation. So you'll get the joke, I'm sure. It wasn't that good, so you don't have to laugh, but you'll get the joke. This is sort of based on some older ideas from the late 70s and the early 80s that embodied by this chip, the InMOS transputer. But the... Yay. So what this chip does is, and what this chip did, is it contains many different cores that all run in parallel, and the idea is that they can communicate with each other, hopefully safely. This chip had some very opinionated ideas about how that should happen, and some very good ideas about how that should happen. This more modern chip, the Epiphany, has some slightly more relaxed ideas about how that can happen. So in the Epiphany, for example, it is possible for any core to write to almost any memory in any other core, which doesn't sound terribly sensible, but it is possible. This chip, I'm pretty sure, could not do, or would not do that. So why does this chip exist? Why did the manufacturers think it was an interesting thing to do? Its main selling point is that it uses very little energy. So it's what's called a system on a chip, and I'm not a hardware person, so I'm not going to explain any of these things in great detail, but the manufacturer's design is such that the number of cores on that chip could be as many as 4,095, but they've only manufactured chips with 16 cores and 64 cores. It runs at about 1 gigahertz, and it runs at less than 2 watts, and it runs reasonably fast, but it has very little memory per core, so 32 kilobytes per core does not sound like a lot. That's for both program and data and any other gubbins you need. So to our sort of modern ears, that's not an awful lot of memory. So that means that compilers and end programmers need to think quite a little bit about how they use this to make it useful. But you'll see that this big board that we have the picture of contains all kinds of other stuff apart from the Adapteva. And this is because the Epiphany chip is really intended to be a coprocessor. So although I said it's a CPU, in some ways it's a little more like a GPU, and it's intended to be used more like a GPU. So the idea is that you have another chip, which is a full CPU, and in this case we have an ARM chip on this board, so it's a bit like the Raspberry Pi. And that CPU runs your operating system and all your other stuff, and it just shuffles data and program out to the Epiphany to get it to execute lots of things that will work well in parallel. So if you were to write a program for this system, you would write two parts of a program. You would write a C program which runs on the ARM chip, which sets up and initializes the Epiphany chip. You would write a program for the Epiphany chip that does the work that you want. So for example, maybe you're doing some image processing or some sound processing, and you've got a workflow that says, well, we make the image black and white, and then we do some edge detection, and then we do something else. Maybe you'd have bits of that going on in different calls, or you'd have whatever you like. So you'd then get your ARM program to send those programs over to whatever cores you want to use in the Epiphany. Then you would start them going and send them data to various shared memory regions in the Epiphany chip. And then the Epiphany cores would all work on that data and do whatever you want, and then eventually they'll finish that work, and then the ARM chip needs to bring the data back. And if you've got large images, I think Robin was talking about terabytes of satellite images if you were in his talk the other day, then you would need to split your very big images into chunks or tiles and send them off bit by bit and slowly assemble a whole result. So this isn't quite the sort of CPU that we're used to. And you'll notice that this board is sort of a little bit like a Raspberry Pi board. You can think of it a little bit like that. So the compiler needs to think a bit, the Epiphany compiler needs to think a bit about how to squidge all of its program and its data into the very small space of 32 kilobyte cores that it's got. And so the compiler does some clever things, but also the chip has some clever things that it can do to help compress that space. And one thing it does is that all the memory is 32-bit memory, but if an instruction can be written in 16 bits, then it'll be written out in 16 bits. So you have mixed width instructions in the Epiphany, and we'll come back to that idea later. So if you were using this board and you were using the Epiphany chip, you might think, well, what would your workflow be like? And you'd probably have one or two practical options. One would be to use the board really as if it's like a Raspberry Pi, so to stick a monitor on it and stick a keyboard in its USB slot and a mouse and use it as a sort of desktop machine with the operating system running on the ARM, which is a bit fiddly, and it means your desk is incredibly cluttered, which I don't like. The other option you'd have is to put a sort of debugging serial cable on the board and stick that in the USB slot of your laptop or your desktop. And so just to sort of shell out to the ARM chip, so to use it like a sort of remote box that you're SSHing into and you only have a remote shell. And that's also a bit of a pain. So a much nicer thing to do would be able to develop all or almost all of your work on your normal desktop using whatever operating system you prefer, and then only use the real hardware when you want to. So obviously I'm not the first person to have thought of this. This is not a particularly enlightening idea. And the chip comes with a whole SDK that the manufacturers have put together, which has its own GCC, its own GDB, its own simulators and so on. But for some perverse reason I thought, well, wouldn't it be nice to write my own simulator for this? And why not do it in something like Python? But it happened that I was just having this thought when this paper came out from a group in Cornell. And this is about writing fast simulators for whatever architecture you like, using restricted Python. So this is the same technology that PyPy is built on. And one of the nice things about this is that if you know about PyPy, you know it comes with a JIT. And a JIT is something that optimizes your code as it's running. So it observes your code running, and if it sees that you've run a loop several times, it will say, well, you've got to the bottom of the loop, and if we get back to the top, instead of running the slow interpreter that's already going, we can create a machine code version of this loop that we've already observed and run that one instead. And that, obviously, because it's machine code, it's really nice and fast. So the PyPy team have built a whole tool chain of this stuff, which creates PyPy, but can also be used to write an interpreter for any language you wish. And these guys at Cornell have created a framework that makes it easy to use all this incredible technology to make instruction set simulators as well. So that's what Revelation does. It's a simulator for this weird Epiphany chip that's written in RPython, which is a restricted subset of Python that can be turned into one of these jittered interpreters. And at this point, most of the instructions are implemented. They're not all correct. So if you if you try this with a real ELF file, you know, good luck, might work. But it's a small code base. There's only just over 1,000 lines of code to make this whole thing work, and there's a lot of instructions in the Epiphany chip. So I think that's quite nice. And if I was going to write another simulator, I would definitely use Pydgin. So if you wanted to do this, what would you do? You would clone PyPy, and that would give you the RPython toolchain. You'd clone Pydgin, which gives you this Pydgin framework that helps you do a lot of the work that you need to do to write the simulator. Put that on your Python path, and then write a simulator. As easy as that. So what bits do you need to write to make that simulator work? So you need all the bits that the Pydgin framework can't know about because they're specific to your particular CPU architecture. So first of all, you need a model for the instructions that you have. So if you think about how a CPU works, I still just work on a very kind of simplistic first-year undergrad module of these sorts of hardware things. So you have a program in memory that's in RAM, and your CPU fetches the next instruction from that RAM. It decodes it to find out what sort of an instruction it is. Maybe it's an add or a subtract or a store or whatever it is. It then executes something somewhere, does some stuff inside the CPU to make that instruction work, and then it goes and fetches the next instruction. So I'm eliding some complexities here about things like interrupts and so forth. So the first thing we need to write a simulator is a model of an instruction. The reason we need this is an instruction is just a binary number. In this case, it's either a 16-bit or a 32-bit binary number. And that number will encode several things. Firstly, it'll encode what sort of instruction we have, whether it's an add or a subtract or whatever. And then if there are operands, it'll encode the operands. So if we're adding something, we might add the contents of register A or register 0 and the contents of register 1 and stick the result in register 2. So we need to get those register numbers out of the instruction. So this is what your instruction model should do. It stores the bits that make up the instruction. It stores the name of the instruction, which I've called a mnemonic, and then it has whatever methods you think you're going to need later on. So some of you who are sort of proper Python people, as it were, may say, well, RD and RM are no reasonable names for methods, and there are several unreasonable names in Revelation, and these come directly from the Epiphany architecture reference manual. So I try to make sure that my code and the reference manual are as similar as possible. And then these methods just do a little bit of bit twiddling to get out the right operands that we need for an add instruction. So now we know how to get the operands out. We need to decode the instruction in the first place. We can't execute anything unless we can decode it. And this is something that would take up quite a bit of effort if you were to write a decoder by hand. And what you'd be doing here is looking at each binary number and saying, does it match the pattern for an add instruction? No. Does it match the pattern for a subtract instruction? No. When you find the instruction, you've got to say, which method is it that implements that instruction? Go and fetch it. And Pydgin provides all of that for you, essentially. So what you need to do is write this big list of encodings. And in this case, I've just left in, for the sake of brevity, one instruction. So this is the 32-bit add instruction. And this says, what does a 32-bit add instruction look like? Every 32-bit add instruction has these particular zeros and ones. And then the rest of the bits we don't care about, the x's we don't care about. The operands will be in the x's somewhere, but then it's up to the function that executes this instruction to find those out. So then we we've called this add32, so in Revelation everything is called something 16 or something 32, so I always know which sort of instruction it is, what its bit width is. Then we need to write a function called execute underscore add32, and it has to be that way so that the Pydgin decoder can find it. And what we do here is just have a little bit of code which gets out the right operands. So this is the Rn and Rm that you saw earlier from the instruction slide. Trims them, which means cut the whole thing down to 32 bits if it's more than 32 bits, and stores it in the register file that's in that operand. So I think the example I said earlier was add the contents of register 0 and 1 and stick them in register 2. This would be register 2 when we've done inst.rd. Then we increment the program counter, 4 steps if we're in a 32-bit instruction, and then we do some other funny bit twiddling, and that sets all the flags, or some of the flags, inside the CPU, or inside the Epiphany. And then once we've done that, and this code is really just copied almost verbatim from the reference manual, we just need to create a RISC decoder somewhere in this module, and then that's it. And all the other work is done for us. So that's really nice. That's like a huge piece of work that we don't need to do. We just need to add these encodings, add these funny functions, and we're done with decoding and executing instructions. So that's great. The next thing we need to do is make a model of a machine. So in this case, we have 107 registers in an Epiphany chip. So very risky if you're keen on RISC versus CISC. Very much a RISC chip. We say what the reset address is, and this is where the first instruction is stored in memory. And it might seem unusual if you're a hardware person for that to be address 0, but indeed it is. And then we create any flags we want and any extra bits and pieces, and we have to provide a function that fetches the program counter so that other parts of the framework know where the program counter is. Lastly, we need to create a model of the simulator itself. And in this case, the example that I've put on the slides is really simple. And that's partly because I've elided some of the sort of more complex things like interrupt handling. But all we need to do here is to call the constructor for the superclass, which is provided by Pydgin. We need a decode function, which does the decoding. So all this is doing here is taking a number that we've pulled out of memory, we've fetched out of memory, giving it to the decoder that was written by the Pydgin framework here. We get back the function that needs to execute that instruction and a string which is the sort of mnemonic for that instruction. So in this case it's add32. And then we need to initialize the state, and this is all the stuff that loads an ELF file or a binary file from memory. So this is the file that was created by GCC. Creates the memory first, of course, and that's provided by Pydgin. Loads the program into memory, creates the whole sort of machine model, and then we do nothing else because the framework provides everything to run the simulation. So that's the basics of how you would use the Pydgin framework. But if you were so inclined to go and look at the source code for Revelation as it is today, you would see it's very different from the quite simplistic model that I've just explained to you. Hopefully I've convinced you that if you ever wish to go out and write a simulator, you could use this framework and it wouldn't be eye-wateringly difficult. But in the case of the Epiphany, things are a bit trickier than they might be for something like an ARM chip or an x86 chip. And there are some various reasons for this, which I'm going to spend some time on. So one is that the chip is basically almost all memory. So there's a flat memory map, which contains all of the memory for all of the cores and some special bit of memory which is called external memory, which is what the ARM chip can write to and from. And everything is a bit of memory in the Epiphany. So a register is just a location in memory. A flag is just a bit inside some location in memory. And that means that the storage model that Pydgin provides doesn't quite work for the Epiphany, because rather than saying, I want a load of register files, which are sort of a separate thing, they're kind of stored like a dictionary, or sort of like a dictionary. And then a model of my RAM, which is a list of integers, say. That's not quite what we want for Revelation, because everything is a flat memory map. We really want to say, if I'm writing to a register, I don't want to be writing to some separate object. I want to really be writing into the RAM. So Revelation has its own storage model, which fits the Epiphany and is very similar to what Pydgin provides, but instead of having separate registers, it just passes anything that goes to a register back to the correct place in RAM. So that's a little bit of an extra hassle. Another bit of extra hassle is that the Epiphany has this really sort of clever way of addressing its memory. So if your chip 808 in hex, then you want to write to address 100 in your memory, then you just say, stick this integer in address 100, and that's fine. But that address 100 isn't really necessarily in position 100 in the global memory map. It's position 100 in chip 808's tiny little segment of the global memory map. So the Epiphany will map these local addresses onto their global addresses. So if you're chip 808, then your position 100 is going to be in hex, OX808, whatever 100 is, following it. So it's sort of all together with your core ID. So this means that sometimes when you're writing to a bit of memory, you're not really writing to the address that you've been given. You're writing to some other address somewhere else. So the memory model for Revelation needs to take account of this and have an extra bit of logic that's going to map everything to the right place, which is a little bit of a pain. But you can sort of see why it's been done, because that means that addresses are very small, which means you're more likely to use a 16-bit address, a 16-bit instruction wherever it's possible. So this is the second thing. There are quite a large number of instructions in the Epiphany instruction set, which I guess is a bit less risky than having 107 registers. And almost all of those have a 32-bit version of the instruction and a 16-bit version of the instruction. And if you were writing a simulator from scratch, you would not be wanting to sort of copy and paste all that again and again and again. You would want to have some nice way to just say, you know, if it's 16-bit, you know, do something almost the same as what we're going to do for the 32-bit version. So most of the instructions in Revelation don't look quite like the ad you saw before. They look more like this. So this is a closure. It's a function within a function in Python. And this is the execute function, which says if we're given an instruction and we're given a state, so a core, a machine core to work on, then first of all, if this was a 16-bit instruction, 0 out its top 16 bits, because we know they belong to another instruction and they're nothing to do with us. And then we've actually doubled up again here. This is a jump instruction which says change the current program counter from whatever it is to this particular number. But as it happens, in the Epiphany instruction set, there are two sorts of jump. There's do it that way, and then there's, but before you jump, please save your current program counter in a special register that's reserved for that sort of thing. So that's jump and link register. So here we say we've got four different sorts of this, four different sort of flavors of this instruction. We've got the 32-bit and the 16-bit. We've got the save the program counter please and the don't bother. And so we put all of that into one function. And then where we have this stuff, we say, well, if your jump and link register 32-bit, then this thing is false and this thing is true, and that gives us back this function with its correct configuration to do the right thing for that particular sort of jump instruction. So this saves a huge amount of duplication, which is really nice. So if you were doing this, you would then compile your simulator with RPython, and .ogit says, please provide me with a JIT for free. And then you'd be able to run it. And then you can iterate and add all your other instructions and make it better. So that's really nice. But before we have a working simulator, we need to probably test it. So most of the rest of this talk is going to be about testing. So I'm only mildly nervous that David is in the front row. So this step I've just showed you, using RPython to translate your RPython code into C and then into a binary executable so it's much faster, is really nice. But that step of translation and compilation takes quite a while. So when you're testing, you don't always want to be testing with your fast native executable simulator. You mostly want to test with your RPython code just as it is, because that makes your workflow very, very much faster. So compiling is slow. But because RPython is a restricted subset of Python, that means you can use any Python test framework you like. So I use py.test, but you use your favorite. It really doesn't matter. So in terms of unit tests for Revelation, there are two things which have really been a positive step change in testing Revelation. So Revelation always started out with unit tests, so sort of normal unit tests which just test a tiny little bit of some code that I've written. Then the Epiphany architecture reference manual, which is sort of a huge document, contains examples for each instruction and some other examples as well. So I take all those examples and turn them into assembler files and use those for the basis of a unit test, which is a slightly bigger unit test really, but it tests one instruction. So there are somewhere over 500 unit and integration tests, but when you think about the size of the RAM that the thing has, the whole chip has like 4 gigabytes of RAM, 500 tests is not going to really test even a tiny corner of the state space of the whole thing. So we have some ways around that, which I'll describe. So this is a unit test which tests the instruction that you just saw, the jump and link register. And this is the 16-bit version of the test. So we've got some different versions of the test, and these run through, and if there's a little bit of time at the end, I'll say a little bit more about how this bit works. But this essentially just gets a new simulator, executes these instructions, these jump and link register instructions, and then checks whether the state that we expect the machine to be in, or the simulator to be in at the end of that execution is how it really was. And we fail if it's not. So that's one way of testing. Another is to use these examples I've described from the reference manual. So this is an example for the same sort of thing. So this is a bit of assembler code, and then we compile that assembler code, and because we have to compile with a cross-compiler and it's a real pain to install, I put the binary file into version control as well. And then we can test this in the same sort of way with py.test. So we use the same kind of state checker thing to say, load this ELF file, run the simulation, and then check to see that we were in the right state at the end of the simulation. That's nice. And that helped me to find a few bugs, but not so many bugs. I started finding a lot more bugs when I started writing C programs and using GCC to translate them to ELF files. So the reason for this is that when you compile with GCC and you compile a C program, you get a huge amount more code that you didn't write. And that's particularly true of the Epiphany, because the Epiphany has no clever hardware to deal with things like the stack or frames or anything like that. So it has a few registers, a few of its, 107 reserved for that sort of thing. But the compiler has to spit out code to manage the stack itself. So that means that each C program that you compile is going to be testing lots more things for you than you might have thought to write in. So a simple hello world like that, we test with py.test again, and what this does is same sort of thing. It loads the ELF file, it runs the simulator, and it checks, in this case, it checks that the output that it saw on standard out was hello world. Great. So that helps a lot. I've caught a lot more bugs that way. I caught even more bugs when I started thinking about using the official Adapteva simulator as a test oracle. So a test oracle is a sort of known truth. We assume that the Adapteva official simulator always gives the right answer to any simulation. Thank you. But here's an interesting problem. The way I would check whether my simulator and the Adapteva simulator both do the same thing, it's quite tricky. I can test that they both write the same thing to standard out. I can test that they run the same number of instructions, but that doesn't tell me very much, and it certainly doesn't tell me where a bug is when I found a bug, which is a real pain. So both Revelation and the eSIM simulator can print a trace of everything they do to their simulators, every change in memory or a register file. This is an eSIM trace file. It's for a test case that I haven't committed yet because it's a feature I haven't implemented yet. It's 4.5 megabytes. It's nearly 50,000 lines, and you probably will look at that and think, ugh, what does it mean? This is the same thing, the same tiny bit of trace from Revelation. It's even bigger, it's even more lines, and it's not much easier to read. So to deal with this, I wrote a script which diffs these two traces, and then it only tells me about the instructions that differed between Revelation and eSIM. So although the result of the diff is not much nicer to read, I'm only looking at things that I need to be looking at. I'm not looking at 20,000 instructions that were absolutely fine. But this is still a little bit tricky, and in fact, this, where are we? Here's an example of an instruction that is speciously different in the two simulators, but correct in both of them. So this is a trap, which is to do with system calls, but I won't go there. eSIM writes a value back to a register. Revelation writes two values back to the registers. Well, that's because Revelation is writing back both a return value and an error code, if there is one, and it always writes 0 for the error code if there isn't one. Well, eSIM doesn't do that. I don't know what eSIM does. Probably something really clever. But that's a slight difference which doesn't matter. There are more differences that don't matter. It turns out that eSIM writes its trace to a file, and Pydgin, the Pydgin framework, by default writes its traces to standard out. Now, if you're like me and you don't think about these sort of OS things very deeply, you might think, well, so what? And I did think so what until I had a really nasty bug. And the nasty bug was really difficult to track down, because when I went through a system call to do something like write hello world, the security mode of standard out was different for eSIM and for Revelation, which is horrible. So to fix that and to remove some of these specious differences, I've had to write my own logger, which means that I always do exactly what eSIM does. I never have those problematic situations. But it also means that there's another huge load of Pydgin framework that I need to replace with my own stuff, because I don't want to be using their logger framework. So what could you conclude from that? Testing is really hard. I haven't tried automated testing, but I probably should. Okay, and that's about it for me. Thank you.
Thank you, Sarah. That was very interesting. And we've got about 5 minutes for questions. So perhaps if we could try and keep them nice and brief, we could have a few questions, because I can see quite a few hands up already. We'll go for the front one here.
I'm not going to ask you about testing, don't worry. What is interesting actually is because the system you're simulating is highly parallel because of the number of cores. Are you just simulating a single core, or do you do the whole thing, and if so, does that cause you any problems?
So I do the whole thing. So yes, it does cause problems. So the main problem was that issue of the global memory map, because if you only have one core, you don't need the global memory map, and you don't care, essentially. But the only sort of slight downside about the multi-core stuff is that there isn't an easy way to use threads in RPython. So what I do currently is just cycle around each core, each core that is still active to run, and execute its next instructions, which is a bit bleh, but you know, it works.
I couldn't help but think in one of your earlier foils, you mentioned the chip had 64 cores, then you said it went up to 4,095, and I wondered what happened to the one core.
Okay, so what I mean by that is that you can buy versions of this chip with 16 cores, and you can buy physical versions of the chip with 64 cores. But you can get the Verilog design for 4,095. And if you have the money to fabricate them yourself, I think, but I'm not sure, that it's because there's a bit of memory that's reserved for communication with the host chip, and I think that's where you can't put it. Yes, but it's mapped wherever it really is. Yeah, you can have a chip. You do have a chip 0 if you want. Yeah, they would, because the memory would be, their memory would be mapped to the right place. Okay. They can, but let's let's not go into the.
So whilst RPython is a restricted subset of Python, there are some things that at least a couple of years ago it didn't implement properly, notably when I was using it closures. Did you run into any issues with the transpiling step with bits that it implemented differently? And also a slightly sillier question, does it still print the Mandelbrot whilst you're doing the transpilation step?
Okay, so the answer to the second question is yes. Oh, that doesn't seem worth it. The answer to the first question is no, I didn't, but I think I was really lucky because I started this just when the RPython team had implemented properties which were ever so useful for me. So, lucky me.
Got time for one more. There's a gentleman at the back I've seen, so we'll just...
You said that the memory model for the chip was outside the sort of bounds of what the Pydgin framework was expecting. Did you have to make changes to that framework, and did you sort of communicate with upstream about it? Were they responsive?
So I essentially replaced it, but really based on the original Pydgin memory model. I haven't asked them to merge it upstream. They are extremely responsive to issues and things. They're really nice, and they're really nice about pinging them with things like, how on earth do I do this? Or I've got this hideous bug. What on earth do I do next? Sort of thing. They're a very nice bunch of people. So I was very lucky there. I haven't asked them to merge my changes because I just don't think that they would be useful for anyone except me. But yeah. I can't quite imagine that there are other chips that work this way. But I'm not a hardware person, so maybe there are. And maybe there's like 20 people who desperately want to write a simulator for. Yeah, the logging change might be more useful. Yeah.
Thanks very much, Sarah, and just if we could all round of applause.